Hello, everyone. We are Team Sensoria, and today we are excited to present our project, a brain computer interface that lets a user control an aircraft simulation using only their mind. I'm Miguel, a medical student at Universidad Peruana Cayetano Heredia.
I am Valeria Rivera, a medical student at Universidad San Martín de Porres here at Lima, Peru.
Hi, my name is Omar Perez Tares. I am medical student at Universidad Peruana Cayetano Heredia. So let's begin.
In healthcare, patients with severe motor impairment face a critical challenge. They cannot effectively interact with digital environments. We propose a way to restore digital control for patients who cannot move in order to increase autonomy and reduce caregiver burden for hospitals, rehabilitation centers, insurers, and families. First, who is the user? Not the patient, but the clinician who interacts with them every day. This includes neurologists, rehabilitation physicians, occupational therapists, physiotherapists, and assistive technology specialists. These clinicians struggle because most assistive devices still require some degree of muscle movement or eye control, which many patients simply cannot provide. As a result, patients become highly dependent on caregivers, communication becomes slow or impossible, and clinicians spend significant time trying to compensate for technology that doesn't match patients' abilities. What they need is a hands-free, accessible, low-cost interface, one that works even when movement is absent. Our target population is very specific: patients with severe motor impairment, such as stroke. These individuals often have minimal or no voluntary movement, fatigue with eye tracking devices, and very limited options for digital interaction. A smaller, clearly defined population help us build a solution with real clinical relevance and immediate utility. To bring any healthcare technology into real-world use, we must ask, who pays? In this case, multiple stakeholders have a strong incentive. Hospitals, neurology and rehabilitation departments, rehabilitation centers seeking modern assistive tech, government disability programs aiming to reduce long-term care burden, insurers, both public and private, and in some cases, families who already invest in expensive assistive devices. All of these groups value the same outcome: greater independence at lower cost. Our solution must deliver outcomes that are both quantifiable and compelling. These include reduced caregiver-assisted digital tasks, higher accuracy of BCI command detection, faster performance of digital actions, improve independence scores on validated clinical scales, reduce clinician setup time. These metrics matter because they directly improve patient autonomy while reducing long-term costs, a win for both clinicians and payers. Our AI model uses supervised learning with a small calibration dataset to recognize the user's mental command patterns. The goal is not perfect accuracy, but to show functional, real-time control and demonstrate feasibility for assistive healthcare applications.
The game starts by clicking Start Session. The objective is simple but engaging. The user must collect 20 coins using only neural control. Coins is going to fall at the top every 4 seconds, and the spacecraft is positioned through motor imagery. When the user performs right hand motor imagery, the probability of moving right increases, causing the spacecraft to move in that direction and catch the coin. Similarly, the left hand motor imagery increases the probability of moving left, allowing the spacecraft to shift left and collect another coin, for example. This interactive approach keeps patients motivated, as they are not merely performing repetitive trials. They are playing a game with a clear goal. The 20 coin target provides a structure and a tangible sense of accomplishment.
Implementation and feasibility. In a real healthcare setting, this system could allow patients with paralysis to control mobility device, communicate, or interact with digital interface using only neural activity. Our deployment pathways include a low-cost EEG set, cloud-on device, AI processing, and plug-and-play interface that can connect to wheelchairs, communication apps on a smart home device. We are aware of limitations, e.g. noise, variable signal quality, user-dependent training, and the need for strong ethical safeguard to protect neural data privacy. However, even in this stage, the level of functionality demonstrates clear feasibility for clinical use case. Our next steps include testing the system with 20 users to improve calibration accuracy, integration additional mental commands to expand functionality, and creating a clinical-grade interface for facial and neuromuscular disorders. We also plan to collaborate with rehabilitation specialists to evaluate usability and cognitive load, and to explore integration with assistive technologies such as wheelchairs or robotic arms. With more time, we will implement deep learning signal decoding, improve artifact suppression, and fuel optimize that user interface. We believe this technology has the potential to significantly restore independence and improve quality of life for patients with severe motor impairment. Thank you for watching. We hope you enjoy our demo of mind control flight and the possibility it opens for the future of healthcare.